So we start off with our channels closed at rest. And it's really important to distinguish that this channel is closed, but it's capable of opening, right? It's capable of being opened. So this is below our negative 55. This is below our threshold. This is at negative 70. And let's say we have a few graded potentials, base sum, and we do get to that threshold stimulus. We are going to depolarize the membrane by opening up this channel. But we want to understand that there are two signals sent during this depolarization phase. There's a signal sent to open this inactivation gate, right? So both of the gates are now opened. And then there's a 1 millisecond delay to close that inactivation gate, okay? We also want to point out here that this is a positive feedback mechanism simply because opening up one sodium channel actually signals the neighboring sodium channel to open up, and that actually propagates down the length of the axon. So the presence of sodium opens up more sodium channels, and we have sodium begetting sodium begetting sodium. So that's an example of a positive feedback loop, okay? And so just to describe those different gates again, the activation gate is only voltage dependent, right? It has nothing to do with time. At a certain voltage, it's going to do a certain thing, and that's the end, okay? It is going to open at threshold, that's negative 55, and it's an example of positive feedback, the activation gate. The presence of sodium opens up this activation gate, signal is sent to the neighboring activation gate, that opens up more and more and more along the membrane. Inactivation gates, however, are voltage and time dependent, right? So they have two signals that they are responding to, a voltage signal and then a delayed time signal. They are open and closed during depolarization. And so the take-home message with this bit is that two signals are sent at that depolarizing threshold, to open, but also to close, okay? Let's look at potassium. Potassium is a little bit more straightforward. There are no separate gates happening on potassium. It's one channel, and it will open at around positive 30 millivolts, right? And that makes sense, right? Potassium is moving out of the cell. That's the direction of its ECDF. And so when potassium channels open, potassium rushes out of the cell, and that is going to do what to our membrane potential? What kind of effect would potassium rushing out of the cell have on our membrane potential? Right, so lots of positive charge leaving the cell is going to make inside more negative, right? So as potassium leaves the cell, we repolarize the membrane. Our membrane potential slowly falls back to its baseline. This makes the cell repolarize, and in doing so, it is approaching the equilibrium potential for potassium, which we know to be very, very negative, right? Negative 94 millivolts. Again here, only one gate dependent on voltage and time, so very similar to the inactivation gate on sodium's voltage-gated channel, but there's only a 1 millisecond delay happening here at that positive 30. So a very similar scenario to the inactivation gate. At positive 30 millivolts, this potassium channel is going to open, but there's a second delayed response that after 1 millisecond, this channel will close, right? We don't want this channel opened indefinitely, okay? And so this is an example of negative feedback in this way. It's gonna get the membrane potential closer to negative 70, which is our set point, essentially, right? It's our set point. Whereas sodium voltage-gated channels are depolarizing the membrane. They're moving our resting potential further away from the set point, and so this is essentially a positive feedback in that way. Okay, we really want to tie this back to things we learned in the previous unit. Okay, so let's look at this illustration. Again, we talked about this earlier on, and I told you we would get back to it. Understanding what's happening here and tying it to those electrotonic events, right? The movement of those charged particles, which is essentially bringing about this action potential. So we know that action potentials take place across excitable membranes. Now we're usually speaking about neurons when we talk about excitable membranes, but we can be speaking about cardiac muscle, which is autorhythmic. It has the ability to fire action potentials as well. And an action potential is a rapid, large depolarization in the membrane. So basically we're going from rest and we're opening up these voltage-gated sodium channels such that the membrane rapidly depolarizes. And we want to understand what rapidly depolarizes mean, right? It rapidly becomes more positive inside because of the influx of this positively charged sodium. We want to also bear in mind that in this upshoot, in this upstroke of the action potential, there's no movement of potassium happening yet. And so the membrane potential looks very close or looks very similar to the equilibrium potential for sodium, because we have mostly sodium channels opening up, the membranes becoming more leaky, more permeable to sodium, and so the action potential upstroke very closely mimics the upstroke of sodium's equilibrium potential. Now in neurons, when you look at the direction of the action potential, it's going to start in the soma, right? We talked about this, where that stimulus is received. And then it's going to propagate down the length of the axon. Now, an action potential cannot go in the retrograde direction. It must propagate from proximal, which is the soma, down to the axon terminal. Okay? And so in that way, action potentials are unidirectional. Okay. So let's walk through the series of what happens during an action potential. We spoke about the gates and we kind of sort of focused in on what was happening at the gates. Let's sort of zoom out and look at what's happening, the big picture, through each of these phases of the action potential. Okay, so we're starting off at threshold or subthreshold, right? If we don't have a strong enough stimulus, we eventually get to -55 and these voltage-gated sodium channels open up, okay? Sodium rushes into the cell depolarizes, and again, by depolarizes, we mean the membrane potential starts to become really positive as all the sodium rushes in, okay? So the cell's more leaky, more permeable to sodium. This is an example of a positive feedback loop because this is potentiating more sodium to enter. Okay, it's very important to understand. So signals are being sent to get us even further away from that -70. And so this is positive feedback, right? We're potentiating those signals. So sodium is opening up more sodium channels, more sodium is coming in. The presence of that higher membrane potential because of more sodium is again potentiating more channels to open up. So that's why this is a positive feedback. Okay, that can be a little bit difficult to understand. This causes an overshoot, right? So this overshoot or this upshoot or this upstroke, as you'll hear me refer to it, is just the rapid depolarization of the membrane because of the movement of this positively charged ion sodium. And then the membrane potential gets to +30. Now it doesn't get all the way to sodium's equilibrium potential, which is +60, right? It never gets to that equilibrium potential. Why not? Why doesn't it get to +60? Why does it stop at +30?
Because the signals tell it to close.
Exactly. So it's a voltage dependent signal. So at a specific voltage, it's going to do a specific thing. And we said that the signal to close these channels happens at +30. So at +30, we physically cannot depolarize this membrane anymore because we've turned off that signal. And this is where this now becomes a negative feedback loop. We have the closing of sodium channels, okay? Let's move along here. We have the closing of sodium channels and we have the opening of potassium channels. And that sort of flip-flops the environment in the cell, doesn't it? Because we know sodium's ECDF, sodium's electrochemical force, wants to push it into the cell. Potassium wants to go out. So if we open up these potassium channels, potassium's going to start washing out of the cell. That's going to flip-flop our membrane potential. And so now we'll start to rapidly decline as potassium leaves the cell. Okay? And that's going to negate that depolarization that we had earlier. So this results in repolarization of the membrane potential, and all that means is it starts to now approach baseline, and so this becomes a negative feedback example. Let's look at the diffusion of sodium against time. Right, when we look at the graphs here, this is sodium's movement, and you can see how it rapidly starts rushing into the cell here, and then rapidly stops as we close those channels. If we look at potassium's movement, we can see that as sodium channels close, right, as sodium is dropping in terms of its diffusion, potassium is at its peak because now those potassium channels are open, potassium is moving in the opposite direction, it's moving out of the cell, and so it's repolarizing this membrane, okay? And then we get back to baseline where all of these voltage-gated channels are closed. We want to remind ourselves here that the leak channels are still open, right? The leak channels are still maintaining that rest, but all the voltage-gated channels close at -70, again, because they're doing a different thing at a different voltage. And at -70, they are closed, right? They are closed. Okay, let's talk a little bit about what an action potential is. We described it earlier as being unidirectional. We also said that it was all or none, right? It's a rapid, large depolarization used specifically for communication. So this is how we can have electrical signals being communicated from cell to cell, from cell to muscle, right? And again, when I say cell here, we're usually speaking about neurons, right? Neurons. And so in a neuron, the action potential is traveling along from the cell body, and I keep saying that, but that's really important to understand. They can only take place in one direction. And we'll look at the exact mechanism of why they can only take place in one direction, but it has to do with those voltage-gated sodium channels, right? So one voltage-gated sodium channel is going to depolarize, it's going to open, sodium's rushing in. It's going to tell its neighboring sodium channel to open up, but then there's going to be a refractory period where this channel can no longer open up. And so that prevents the action potential from spreading in the retrograde direction, right? It has to go in that forward direction from soma to axon terminal. Okay, now if we divided this action potential, we divided this, the sequence of events into two sort of phases. We'd see depolarization and then repolarization. And we could also sort of associate those two phases, again, a positive feedback and a negative feedback. And in terms of looking at this on this graph, we can see that here. And we can see what ions are responsible for each phase of this action potential. So let's start here. We have a depolarizing stimulus, which we said could be many things. It could be a tactile stimulus, it could be an auditory, olfactory. The way that our neurons speak to each other, the way that we perceive the world around us is through these signals. So the stimuli that set these signals off can be a whole host of stimuli from physical interaction, right? We set the stimulus off and then we open up voltage-gated sodium channels because the membrane is now beyond -55. Beyond threshold. And we depolarize the membrane, which brings sodium in, and then the presence of sodium further depolarizes the membrane, okay? And as such, this is a positive feedback loop, okay? From -70 up to +30, we're going further away from our set point. This is a positive feedback loop, right? Let's look at the second half of these events here. So at our +30, things take a shift. The sodium channels close, the potassium channels open. And so we have the membrane potential drastically becoming more negative. Now this is an example of negative feedback because we are returning the membrane potential back to -70, which is rest, okay? Very important to understand that here. Any questions at this point? Any questions? Any questions? Mm-hmm.
So those positive and negative signs, those are positive and negative feedback.
Right, the positive and negative feedback, right? Because these are both positively charged ions, okay? But we do have them moving in different directions. That's why they're bringing about different influences on the membrane potential. Right, sodium's coming in, it's going to make the membrane potential more positive. Potassium's going out, it's going to make the membrane potential more negative. Okay, and right, going all the way back to speaking about why they ended up moving in those directions, we talked about the resting membrane potential, we talked about establishing the electrochemical driving forces, right? So we know why they're moving in the direction that they're moving. Okay, so let's speak again. We're going to go through this in several different ways, so this may seem very repetitive, but it's only so that you understand this from all aspects, right? So that you understand this in terms of the permeability of the ions, in terms of the membrane potential, in terms of the channels and what the channels are doing. Okay, so we're going to go through this again, but we're going to here be looking at the permeability of the membrane to our varying ions, and we're going to look at how the permeability changes for sodium and potassium as this action potential progresses. So we start off again at rest. We know that the membrane here is more permeable for potassium than sodium, and it's closer to that -94, which is sodium's equilibrium potential. Very far away from, I'm sorry, I'm mixing up my ions. So it's further from sodium's equilibrium potential, closer to potassium's equilibrium potential at rest. Okay. We have a few graded potentials coming along. Now, these graded potentials can be varied, and we'll talk about this, right? An action potential is an action potential is an action potential. If we have 5 graded stimuli, if we have a very strong stimulus, a very weak stimulus, that really does not matter. Our action potential will always be the same magnitude, will always be the same amplitude, will always be the same duration and time, even if our stimuli are different. That's really important to understand. So we can have any number, any combination of graded potentials. As long as we get to -55, we're going to fire the very same action potential that we would fire even if we had a different stimulus. Okay? And so what we'll see here is that the action potential curve very closely mimics the equilibrium potential or the permeability for sodium. Right? And that's simply because we have rapid opening up of those sodium channels. So as sodium channels open, the membrane potential starts to mimic the potential, the equilibrium potential for sodium. And we can see that in the upstroke of this graph. If we look at potassium's permeability, okay, if we look at potassium's permeability, we'll see that again, as sodium's permeability decreases, potassium's permeability is slowly rising, and it's going to peak at this midpoint of sodium's closure, right? The closure of those sodium channels. And then it will also decrease as we repolarize the membrane, okay? So we have rapid opening up of sodium channels. This is a regenerative mechanism. And by regenerative, we mean that it's going to happen again and again and again. If the conditions are made right, it will happen again and again and again. But it cannot happen in the refractory period. That's important to distinguish. Outside of that refractory period, as long as the conditions are made suitable, we will continue to have action potentials. Action potentials are unidirectional. We said that before. They're self-limiting, meaning that they provide the conditions to start, but then they also provide the conditions to end, right? They have a positive, negative feedback balance. So they are self-limiting in that way. And then they're regenerative, we said here. So we have slow closure of sodium channels and slow opening of potassium channels. And so opening these potassium channels and closing the sodium channels, which happens at this +30, is the reason that action potentials never get to sodium's equilibrium, right? This voltage is setting off a different signal for these channels. Okay. So here again, we have potassium channels remaining open, but the membrane, let's jump ahead here actually. The membrane potential is falling, and then it's going to actually go a little bit below the resting membrane potential. And that's because we have this efflux of potassium. And so we're rapidly decreasing in terms of our membrane potential, in terms of the value of the membrane potential. But we pass resting because so many of these potassium channels are open, and we have this efflux of potassium that is rapidly making the membrane more negative, such that it actually goes below the resting membrane potential, below that -70. And you can see that here. It's going to go all the way down below that resting -70. And so what happens here is that it becomes very close to potassium's equilibrium as it hyperpolarizes, but the sodium-potassium pump kicks in and restores that membrane potential back up to rest. Okay, so the ending events of the action potential are such that things are kind of out of whack, right? We're not going right back to rest. We're actually going below the resting membrane potential. And then the sodium-potassium pump has to kick in for a little bit to get things back to resting membrane, right, to -70. So we actually overshoot the membrane as we hyperpolarize. Okay. So again, we go down to about -85, -90 or so. As these potassium channels are opening, potassium is moving according to its ECDF. And then we have those potassium channels closing, sodium-potassium pumps, and the leak channels, right, that pump-leak system, kicking in to even out the membrane potential again.